Okay, between our class, we did a lab, and we said that we have a ruler, and a lot of times we put that pivot point in the middle of the ruler, and that made it convenient for us. What could we ignore if we put the pivot point in the middle? What was nice about being able to put the pivot point in the middle? Yeah, the mass of the ruler didn't really matter too much. Here's the crazy thing. If we looked at the last one, is it number 3? Where you have a heavy weight here, and then you move your pivot point close to it, and then you have something lighter way out here. What's going on here? We have gravity pulling down on the left side. We have gravity pulling down on the right side, and we could add this with this. And you worried about your pivot point being here. That is because what is the pivot point actually doing? What did this brace actually do? It held it not just in place, it held it, wait, what direction? Up. This pivot point literally pushes up. When we're talking about all the sum of all the forces, we're holding it up in one place and down in 3. Okay, so this upwards force should equal the force down plus the force down plus the force down. If we were talking about its rotation, does this upwards force apply any rotation to us if this is our pivot point? No. And so this would be a counterclockwise force while this is clockwise and this is clockwise, adding to it, right? Here's the crazy thing. Was it moving? Or should it be moving if it's balanced? No. So what happens if I pretend and I judge all of my motion off of the middle still? I guess I would have put that right here. Or anywhere on this ruler. If I put it at 40 centimeters even, not in the middle still, is it going to rotate clockwise or counterclockwise? Did it? If I judge it by this one point, I've got 2 things going clockwise. This one's also going clockwise, but this one was the heavy one. This one provides enough downward force for it to also not spin around this point. It doesn't spin around your pivot point, but it doesn't spin around this point, and it doesn't spin around this point, and it doesn't spin around this point. And even way out here, if I were to have a point not even on the ruler, this would push clockwise, 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 but this upwards would be strong enough to counteract the other 3 counterclockwise. So what's going on is I can move my pivot point anywhere technically. The best place to put our pivot point is where we have the least amount of information. Okay? We'll see that happen today. These problems, torque at an angle problems, the pivot point becomes kind of obvious. If I were just to draw it's not really a free body diagram, but if I were to draw a diagram just on this diagonal stick, we're going to need to find the tension to maintain the rotational equilibrium of the fishing pole. We're going to disregard the mass of the fishing pole. What's holding us down? What's my forces acting on this stick? Gravity of the fish. We don't have any pull gravity, but we have what other forces acting on this? All of our free body diagram forces. What else would happen? Force normal. That's the ground holding up the stick. I'm going to pause it real quick. So we have force normal. What else do we have? Find. Do we have what?
We have a pulling force that's holding it against the wall.
So we have the tension of the string. We have one more force. If these were the only 3 forces, it would slide into the wall harder and harder and harder, and it would go through the wall. It would face through the wall, except for the fact that the wall pushes it back. Now, conveniently, we could talk about these forces because your downward force should be equaled out by your upward force. Your horizontal force this way should be equaled out by your horizontal force that way. Because is this fish moving? No. And so all of your ups should equal your downs. All of your lefts should equal to your rights. But what are we talking about today? We've stopped talking about just up and down and left and right. We're talking about angles. So counterclockwise versus clockwise. Okay? So if I don't want to worry about some of these forces, where should I put my pivot point? If I'm rotating, I should put my pivot point on the ground, because if my pivot point is right here, this up arrow does nothing to rotate. If I put my pivot point here, this arrow to the right does nothing to rotate that, right? And so if I'm talking about the net torque, all I have to worry about is this downwards pull and this leftwards pull. And my net torque equals 0, and therefore I can say my leftwards pull should be balanced out by my downwards pull. My leftwards pull is the tension in the string, so it's a positive pull, counterclockwise, right? Positive, counterclockwise. Tension. Tension times the radius of the string times sine theta, and I'm going to call it theta 1, minus, what are we subtracting out? The gravity of the fish. Force of gravity of the fish times the radius of the fish times sine theta of the fish. That's sine theta 2. Why theta 1 and theta 2? This is a full triangle, and you can say that the two angles add up to 90, but this is the complementary angle, okay? So whatever angle this is the opposite of it. And we could figure that out right now. Here's a similar triangle with a length of 2 and a width of 1.2. You could find out that this is a inverse sine problem, right? If I'm looking for this angle, or an inverse cosine problem if I'm looking for this angle. Inverse sine of 1.2 over 2 gives me an angle of, I think, 36.9 degrees. I'm doing this in my head. It's been a while. I should have this memorized by now. But this is then 53.1 degrees. Yeah, that's feeling more confident. And if you didn't do this, it's because you noticed that this would be the 2 or 20 would be a proportionate of 5, while the 1.2 is a proportion of the 3. It's a 3, 4, 5 triangle. And I knew that just because I plugged it in. I saw those angles, and I'm like, oh, hey, look, those angles feel familiar to me. You probably don't have that going on in your head. So if you just do inverse sine, you'll find those angles. Yes, one sec. How do I know what angles to use? So I'm going to find the angle from this vector branch, this displacement right here. And so this string is coming from that way. And so I would say here's theta, and that would probably be theta 2, right? No, that's theta 1, right? Because I've got a parallel lines, and this one's bisecting it, so this angle matches this right here. Whereas the fish is the opposite of it, because it makes a full triangle right here. And I can say, hey, look, that has to add up to 180, and this is 90, or that these two angles add up to 90. Okay. And so that would be my angle number 2. This 36.9, by the way, is angle 2, right? It's like a whole bunch of the geometry proofs that we did 4 years ago, 3.5 years ago for some people. It's been a while. Here's the crazy bit that confuses people. I'm going to say that my tension of the string is what we're looking for. What's the radius of the string? How far is the string from our pivot point, P? 2 meters? I like that. And then we said sine of angle 1 or sine of 53.1. I'm kind of like a little cheater. I'm going to say that it's not sine of 53.1. I'm going to say that it is sine of, it's 4 over 5. Is that true? Yeah. 4 over 5. Remember I hinted that it was a 3, 4, 5 triangle? And so sine of the angle would report back the ratio of the 3, 4, 5 triangle. I'm kind of like lazy and I don't want to plug it into my calculator. You could type it right here. You could still say sine 53. In fact, I'm going to put that right here. Sine of 53.1. Should report back, if all you did was type in sine of 53.1, should report back 0.8. If that's confusing to you. Right here, I'm going to say minus FG. No. What is FG? So 3 times 9.8. And at what radius is it at? Not 1.6. 3.6. Good correction. It's the 2 plus the 1.6. And lastly, I'm going to say sine of angle 2, which is just 3 over 5. Oh, sorry, not sine of 3 over 5. It is 3 over 5. 3 over 5. If you type in sine of 36.9 or cosine of 53.1, it should give you back 0.6. Ish, because these are rounded values. All right. It's just math from here. What do you want to change this minus sign to? Equals? You could say this side equals that side. If it all equaled 0, right? This previous step was equal 0. So that's a minus sign. What else do you want to do? I canceled out my 5s, but then I just plugged it in the calculator, honestly. Yeah, I just multiply and divide. Yeah. I got TS equals... I'm waiting for y'all to say... Oh, there's the bell. 39.7 newtons. I agree. All right. And that's because the tension in the string is offset so that the fish isn't rotating from this pivot point or any other pivot point at this point. The ladder. What are the forces on this ladder? Read through the problem. I'm going to pause the video so y'all can read through it. And we're back. What arrows do you want me to draw?
One showing that the wall is exerting force on the ladder.
Yeah, the wall is exerting a force on the ladder. And it talks a great deal about how we don't care about it getting stuck to the wall. There's no friction like that.
Then we have the force normal of the floor.
Okay, so force normal of the floor pushes up. Where does gravity push down? Not in the center, not in the middle. It says that it's at 0.4 L. So this is the length right here. 0.4 L. And that is 200 newtons down, right? Is there one more force? I feel like there's one more force because I've got an up arrow. I've got a down arrow. I've got a left arrow. I'm missing a right arrow. What is that? Force friction along the ground. This up arrow I'm going to call force normal. This down arrow I'm going to call force of gravity. This arrow I'm going to call the force of the wall. I had somebody say normal force of the wall. You're not wrong. I just want to make sure that we have a different letter between force normal and force wall. Okay? They're both normal forces. You're absolutely right. I just picked something that made sense. And I didn't want to say force floor because we already have force friction. All right. So, statics. Nothing's moving. Okay? Where do you want to start? Anywhere. I'm good with anything. All the torque is 0 across anywhere. Where do you want your pivot point to be, though? On the floor. The floor makes sense. People said the floor makes sense because this is the angle of 50 degrees. Well, that means this is the angle of 40 degrees. That's not crazy. The reason why I started with my pivot point along the floor, it has the most forces happening here. And so when I write out my torque equation, my net torque equals the two other forces that are rotating, not on this pivot point. Force of gravity is negative. So I could say negative mg. That's 200 together, right? For Fg. Right there. Times r. What's the radius of that? Where is the mg located? 0.4 L's. And then we need the angle. Is it 50 or the complementary angle? Right, so I'm going to put sine 40. And what is spinning it the other direction? The wall. Plus, how do I describe the force of the wall? I'm going to put that it is force of the wall, RL, right? The full length. Sine 40 or sine 50? Sine 50? Yeah. That has to add up to 90. Alrighty. And this all works out because our net torque is 0. Okay? So 0 equals this, which means I can switch gravity to the other side. I could say that the force of the wall, L sine 50, equals 200, right? That's mg. 0.4 L sine 40. So the force on the wall, wait, what happens? I'll give you a hint. What happens? L's cancel. Good. So FW equals 200 times 0.4 sine 40 over sine 50. FW. We could find FW. How does that help us? I don't even know, man. Did it even ask us for FW? We need the friction force. You're telling me that the net forces in the x direction equals 0? Okay, so you're telling me that the force on the wall minus the force friction equals 0. So you're telling me that the force friction equals the force on the wall. You're missing one more thing. It's asking for the coefficient of friction. What can we say about the force friction? Oh. What do we know about the force normal? The net force in the y direction equals ma. Yeah, same thing. Because we know it's not accelerating. So you're saying the net force in the y direction equals 0. I'm saying it's ma, which the acceleration is 0. Same thing. which means that the net force in the y direction. Wait, I'm supposed to say 0 there. What are the two things that make up the net force in the y direction? Force normal minus force gravity equals 0. So force normal equals that mg that we were talking about. So right here I can say, instead of mu force normal, I can say mu force gravity equals force on the wall. Force gravity is 200. That's not a mystery to us. Force on the wall is 67.1. This is 67.1. So I have mu equals, yeah. And this is 2/3 of 100, so this is 1/3 of 200. And you said 0.33-ish, 336. Cool. Is there a unit for mu? Alrighty. So if I were to table this out, we used all of our parts. We said that the net force in the spinning, wait, that's net torque, right? Net torque is 0. It's neither moving around and around clockwise or counterclockwise. One of the parts says we're neither moving up nor down. One of the parts says we're neither moving left nor right. We put them all together to talk about this problem, just to find one simple piece. Will your test be this hard? I don't know. It's possible. Let's go back to the practice. You think the first practice problem is going to be that hard? Let me set you up for success. This one, we're going to want to say that the net torque is the torque of the hand minus the torque due to gravity of the pull. So I could have put gravity there. And all we're looking for is the force of the hand, which happens to be perpendicular. I don't think we're going to have to work that hard for some of the problems, okay? But I do think that there is a difference between the way I would expect the depth of problems being in the multiple choice versus the FRQ, right? Hint, hint, nudge, nudge, wink, wink. Make sure that you not only get through the FRQ that you picked up, that you get through the quest homework. Those are things that are due for a grade. But right now, I would try to get more of these packet problems done, so that way you can ask questions while I'm here.